everyone. In this video, I'm going to walk you through from my hardware software co-design project, which is done by me, Muskan, and my partner Guru, where we use a AES 128 core on FPGA and control it from the HPS. The way we divided it is that I took care of the software part and my partner Guru took care of the hardware part. So he developed the RTL file while I developed the main.c file. And then he also took care of the quartus synthesis. And at the same time, in order to verify that the hardware file worked, I came up with a test bench to verify that. And then Guru tested it out on the FPGA. So during the video, you'll find our voices in alternate pattern here. And I'll now start the explanation of the main.c file. So as you can see here, these are all the header files that we included and we'll be using them. This is the header file which has auto-generated the various PIO base addresses that we added as part of the QSys platform designer. Next, I have defined the LW bridge base and LW bit span. These contain constants, tell the program where in the physical memory the lightweight HPS to FPGA bridge is located and how big that region is. The next we have is the number of 32-bit words in the state, a number of bytes in the state. These are AES constants. The next are big lookup tables of the subbytes that I have for AES encryption as well as for AES decryption. Next, I have declared a global array, W60, which holds the expanded key. I believe AES 128 only needs 44 words, but it reserves 60 so that it can support bigger keys as well. NK is the number of keywords, so it's usually a set of 4. And then there is NR, which is the number of rounds, so it is 10 for AES 128. The next function is function mul, which implements the multiplication of the AES Galois field. This is also used inside mixed columns and inverse mixed columns functions. Then we have all the standard AES transformations such as subbytes, which applies the S box to every byte of the state. There's an invert subbytes, which uses the inverse S box for decryption. There is a shift rows function which rotates each row of the state to the left by a certain offset. There is invert shift rows which reverses that rotation and rotates it in the opposite direction. There's also a helper function that we added here called dataget, which extracts a single byte from the forward state based on the byte index. Then we have mix columns, which applies the AES column mixing, and there's inverse mix columns, which does the inverse of that operation. There is add round key, which XORs the state with the appropriate round key. And then we have key schedule helpers such as subword, rotate word, key expansion, and cipher. Cipher is one of the functions which actually implements AES encryption. So it has initial add round key, it has multiple rounds, and then a final round without mixed columns. And then there is another function which is an AES decryption function which call at invert cipher, which implements the AES decryption, and all of this together is basically a full compliant AES 128 implementation in software. All this code we have already we've taken from the AES 128.c file that we compiled during one of our homeworks, and whatever lies next is what we have added to implement this. So first thing is print ct concat function, which is a helper for printing as well as packing. We have this because it takes 432 bits words C0 to C3 and prints them as one 128-bit hex string in the order of C3, C2, C1, C0. So it is just to make the ciphertext look nice and contiguous. Next is the pack state function. It takes 16 bytes, it packs them into four 32-bit integers. Each 32-bit word looks like B3 left shifted by 24, then left shifted by 16, 8, and so on. This is the exact format the AES code expects the state to be in. And then there is our actual main function, which is our main HPS program, which opens the dev memory and the maps the FPGA. This is the dev memory opening function. And then we set up a few pointers here for key 0, key 2, key 0 to key 3, which is each a 32-bit register mapped to FPGA. Then there is plain text 0 to plain text 3 registers. There's a start register, there's a done register, and then there is ciphertext 0 to ciphertext 3. Here, start and done are the control and the status bits to trigger encryption and wait for its completion. And next is we generate a random key using the random function here, supported by C. For the plain text, we create another 16-byte array and zero it with memset, and then prompt the user to enter 16 up to maximum 16 characters. We also pack this plain text into data software 4 using pack state, and this is a software representation. So what we do is we pack this plain text into data software. Then there is packing of the key into four 32-bit words, which is key 3, key 2, key 1, and key 0. Which means that the key 3, K3 contains the first 4 bytes of the key in big Indian order. And we write those 4 words into FPGA registers right here. So now the AES core inside the FPGA has the full 128-bit key. And then we do the same packing structure for plain text as well, and we also write that plain text into the equivalent plain text register. We start the AES core here, and it is designed to detect the rising edge of the start, and it loops until the least significant bit of done is set to 1. Once done is high, we read the ciphertext from C3, C2, C1. Ciphertext 3, ciphertext 2, ciphertext 1, and ciphertext 0. And we get back the byte form. We split each 32-bit words into 4 bytes and store them in capital C16. So we get each 32-bit words into 4 bytes. And then we have a software decryption using the same key. So first we call the key expansion. So this computes all the round keys and populates the W array. And then we declare data decode 4, fourth index, which will hold the ciphertext back in the AES state format. And then we pack the 16 ciphertext bytes C16 into 4 words using this function. At this point, the data decode contains exactly what AES software expects as the encrypted block. Then we call the invert cipher function. This runs the AES decryption algorithm and using the round keys. And then after we call this, the data decode would actually have the original plain text post the decryption. This is just a debug statement, so I'm just gonna comment it out. We tried printing out at each and every step of the design so that we know what we are actually getting as the output and if we are going in the right direction. And then we convert these 4 words back into 16 bytes, and we just um, extract each byte out of it. The last part of it is the printing the results. So we print the encryption key, we print the original plain text, which was exactly as what was typed by the user. We get the ciphertext from the FPGA after concatenating it in the big Indian format. So finally, we print the plain text recovered from the software decryption and its equivalent bytes as well. Um, and we unmap the LW bridge and close the memory and return back. So yeah, this is all about the AES-128 encryption and the decryption along with the FPGA design that we came up with. Thank you.
So Muskan explained the HPS part of the AES encryption. Now I will be explaining the FPGA part of the AES encryption. So before going through the Verilog code, let's have a look at the platform designer first. So we can see here the HPS underscore 0 is the HPS of the Cyclone 5, and we have created 14 programmable IOs. So four programmable IOs for key, and similarly 4 for plain text and 4 for ciphertext, and one is start to let the FPGA know that the key and plain text is ready, and one is done, which is to let the hard processor to HPS to know that the encryption is done. So we can see here all the S1s are connected to the master of the Axilite bus here, this one, and we can also see that the all the conduits are exported. These conduits will be seen in the Verilog file. So let's look at the Verilog file. So here we can see all the exported conduits. CT is the ciphertext which is input to the HPS, and also we can see the plain text, the start and the dunce, the key. So these are all exported from the HPS platform designer, and this is our Verilog top module. So here we can see all these things. So here we have instantiated the AES core. So this is the AES core, but this is where the actual encryption is done. So let's synthesize this. The code is synthesized with 0 errors, and you can see the resource utilization as well. Yeah, this is the resource utilization, so you can see the total number of ALMs, ALUTs registers, the IOs, and the HPS used. So we had several issues in implementing the AES core on the FPGA. So now Muskan will explain how we overcame those issues.
So in this part of the video, I will be going through the test bench part of the project that we developed. So we were facing a few issues when we tried to dump the both hardware and the software part of it to the FPGA, since we were seeing only the software part execute. So that's why we wanted to check if our hardware also works as a standalone part or not. And so we developed this test bench. The motivation and the inputs of the test bench are very simple, and they were already the ones which we had already done in our previous homework for the software part. So we put the same input to get the expected ciphertext. So the way it goes is we implemented a task here which had four inputs, which had the key, the plain text, the expected ciphertext, and label is just for a tiny ID, which we added because just in case the test cases increased, we asserted the start bit for one edge of the clock, and then we waited for done to be 1. Once the done was 1, we displayed the ciphertext as well as the expected ciphertext, and at the same time displayed if the result was right or wrong. The way it worked is we in this initial block, we called the run test task in which we first gave the key, the second as the plain text, and the third was the expected ciphertext, which we already knew from our previous homework. And that's it. This is the simplest test bench that we developed just to check if this particular code works. And for it, this is the same code that Guru used and Guru developed to synthesize in Quartus as well.
Now the board is booted with Linux, and the board is connected using a UART to the Teraterm here. And we have also programmed the FPGA using Quartus. So now let us verify design. Yeah, we can see here the encryption key is auto-generated, and the ciphertext from the ciphertext generated on the HPS and the ciphertext from the FPGA are same, and the decryption which is happening on the HPS gives us the exact plain text. So the design is working. That's all. Thank you.